Hello, my name is Juan Paredes, and today I will talk about stabilization of thermoacoustic oscillations in a Rijke tube. This presentation will be complemented by the laboratory demonstration that we will go through afterwards. Self-excited systems are systems that yield an oscillatory response under constant input. The coupling between acoustic fluctuations and heat release rate fluctuations may give rise to thermoacoustic oscillations, which may cause flameout, structural fatigue, and loss of combustor performance. Although some systems are designed to minimize these effects within a range of operation, changes in operating point and field property variations may still cause thermoacoustic oscillations and flameout. The present work considers the use of adaptive active control to suppress thermoacoustic oscillations under different operating conditions. For demonstration purposes, a Rijke tube experiment will be considered. In this presentation, first, we'll briefly introduce the Rijke tube experiment. Then we'll introduce a nonlinear Rijke tube model, which will be used in numerical examples as a preliminary study of the stabilization performance of the proposed controller. Next, we'll discuss the real-time control architecture considered in this demonstration. Then we'll introduce the adaptive control law considered in this presentation and in the subsequent laboratory demonstration. Next, we'll discuss the results of implementing the adaptive control law in the Rijke tube model introduced at the beginning. Finally, we'll introduce the Rijke tube experiment built in our laboratory, and we'll briefly discuss the demonstration test we'll perform after this presentation. The Rijke tube consists of a heating element placed inside a tube of heat-resistant material, such as metal or glass. Pressure oscillations can be created by supplying energy to the heating element. According to a Rayleigh criterion, vibrations are encouraged if heat is given to the air at the point of highest compression or extracted at the point of highest expansion. The opposite is also true. This implies that oscillations can only form if the heating element is placed in the lower half of the tube. Furthermore, this implies that oscillations form the easiest when the heating element is placed at the lower quarter of the tube. Reference 1 provides a more in-depth explanation of this. Oscillations can only be maintained under constant heat supply and disappear after heat is no longer supplied. Furthermore, a minimum amount of heat needs to be supplied to overcome the acoustic damping of the tube. The sizing of the tube and the shape of the heating element need to be considered as well, but we won't discuss this during this presentation. A speaker, a microphone, and a digital controller are considered in this work to stabilize the oscillations. Now we'll present the Rijke tube one-dimensional nonlinear model, which was derived by combining aspects from the nonlinear model in references 2 and the linear models in references 3 and 4. XU and XD will denote the distances of the coil to the bottom and the top of the tube. XMic will denote the distance from the microphone to the top of the tube. Upstream and downstream values in the model will be denoted by subscripts 1 and 2 respectively. Furthermore, F and G represent acoustic pressure propagation within the tube. A block diagram of the whole model is now being shown. Q denotes the heat the coil section, and U1 denotes the airflow velocity at the same place. Furthermore, the model features some time delays, whose values depend on the position of the coil and the microphone, and the mean wave speeds within the tube. The model also features a linear map F, whose X and Y matrices can be considered constant due to the low Mach numbers of the application. The psi function is a biased smooth saturation nonlinearity that limits the effect of the feedback between the heat and the airflow velocity near the coil. This is a modification introduced in the models in references 3 and 4, and based on the model in reference 2 and our insight on nonlinear oscillators. The input of the model V is the speaker pressure, and the output of the model Y is the microphone pressure measurement. Here are slides of the parameters used in this model and the values used in this work. Some of these were chosen to match the experimental setup, while others were chosen so that the free response of the system under no speaker modulation matches that of the experimental results. Here is a comparison between the resulting oscillation from the proposed model with the parameters shown in the previous slide and the Rijke Tube experiment in our laboratory for a single operating condition. While the fit is not exact, we'll later show that the model is accurate enough for preliminary testing. The objective in this case will be to suppress the thermoacoustic oscillations measured by the microphone by modulating the speaker output, which is formalized by the formula on the screen. Now we'll go over the control architecture implemented in this experiment for real-time operation. The physical or simulated systems presents the system that we want to control. In this case, this represents the Rijke Tube experiment. Sensors are used to obtain measurements from the system in the form of a voltage signal to gain information about the system. In this experiment, the microphone will be used as the only sensor. Then the control algorithm will use the measurements and yield the input signal required to control the system. Finally, the actuator uses the voltage signal from the control algorithm to act on the system and modulate the system response. Note that the control algorithm is implemented by a computer program. Since the algorithm is implemented in a digital computer, a sample time implementation is required. In this setup, a step is taken every TS seconds, which is the computer sampling time. The number of steps is denoted by K and will be used as a subscript when referring to signals that change at each step. Note that while the control algorithm obtains measurements Y from the microphone at the current step, the system input V it calculates for the speaker is only implemented in the next step. The control algorithms we will discuss today take the form of digital controllers. At each step K, the output of the controller is given by the displayed formula, where C represents a performance variable and V is the input of the system and the output of the controller. And LC is the controller order. The objective of the controller is to minimize the absolute value of C as the number of steps increases. In most cases, C is the difference between a reference signal and a sample measurement. The controller's coefficients determine the behavior of the digital controller. As a simple example, consider the system described in the following equations of motion. In this case, a digital controller with a sampling rate of 0.05 seconds will be used to modulate the system input V, such that the measured output reaches 1. As you can see, while all the displayed controllers reach the desired output, the coefficients of each controller determine how this objective is met. However, changes in the system parameters may cause the controllers to behave in different manners. Hence, some parameter tuning is often needed for different operating conditions. The adaptive flow we propose next addresses this by determining the controller coefficients in real time. Retrospective cost adaptive control, or RCAC, is considered in this work. As before, the output of the controller is given by the displayed formula, where CK is a performance variable, VK is the output of the controller, and theta is the set of controller coefficients. In RCAC, theta is updated at each discrete step with the purpose of minimizing a retrospective cost. Note that the information known to RCAC is in blue and the updated variables are in red. The retrospective cost is given by a quadratic cost function in theta and is convex, which means its minimizer can be very efficiently computed using recursive least squares. Note that the regressor phi and the previous controller outputs are filtered by GF, which is a filter that encodes the information required by RCAC about the system and whose components depend on the application. As was mentioned before, due to the quadratic and convex structure of the retrospective cost function, a closed loop solution for the optimization problem at each discrete time step can be determined via recursive least squares. At each step, the data is filtered by GF. Then the control parameters, that is theta, are updated, and the recursive least squares covariance is propagated. Finally, using the regressor and theta, the control output is computed. Note that the controller and the adaptation can be enabled and disabled. When the controller is disabled, the output of the controller is forced to 0, And while it is enabled, its output is given by the formulas in the previous slides. When adaptation is disabled, the value of theta is kept constant at the last value obtained before it was disabled. Otherwise, theta is calculated as shown in the previous slides. The capacity of enabling and disabling the controller is useful when we want the controller to act only when a certain operating condition has been reached. Disabling adaptation is useful when one wants to use the last value of theta for a static controller. Since RCAC is a discrete time controller, a sample data implementation must be considered. The controller and the discrete input are both updated at each sampling period Ts. Also, the performance variable mentioned before is the normalized error shown in the slides, where nu is 0.2. A reference of 0 is used in this work to reflect the desire to suppress oscillations. For comparison, note that RCAC can be used to control the simple system studied before and to obtain controller parameters that can be used later to yield a similar performance. In this case, RCAC determines the value of controller coefficients A and B for the first plant. And for the second plant, it yields a different performance than that of the static controller. The performance is similar even under changes in the system parameters, in contrast to the controllers with static coefficients. In the following numerical examples, the objective will be to stabilize the oscillations in the Rijke Tube nonlinear model. We'll consider 3 cases in which the coil will be placed in different positions. The controller will be enabled at about 2.5 seconds from the start of the simulation to wait until an oscillation forms within the model output. Adaptation is always enabled, and the RCAC parameters shown at the bottom of the slides are kept constant throughout all of these examples. The sampling rate of 1000 Hz was chosen since the frequency peak of the measured oscillations is below 250 Hz. The controller order of 5 was chosen since 5 discrete steps at the chosen sampling rate can cover most of the period shown below. The P0 and RU hyperparameters were arbitrarily tuned. In all cases, under the same hyperparameters, RCAC manages to suppress the oscillations of the Rijke Tube nonlinear model. Note that each operating point required a different speaker signal for stabilization, as well as different steady state coefficients. Now, we'll briefly introduce the Rijke Tube experiment implemented in our laboratory. This experiment is composed by a nichrome or cathode coil being supplied electric energy by a variac, a lavalier microphone connected to a preamplifier, a speaker connected to an amplifier, and a Calexio digital controller with ADC and DAC components that implements RCAC. Note that the RCAC parameters in this experiment are the same as the ones used in the Rijke Tube numerical examples. The open loop pressure waveforms measured by the microphone are shown for different coil positions and supply voltages. For the experiment, XU is the position of the coil from the lower part of the tube, and VRMS is the RMS voltage supplied by the variac to the coil. As seen in these figures, the frequency content of the system response is different for each operating condition. We'll later see that RCAC is able to suppress the oscillations in 4 of these cases, the corner cases. Before we end this presentation, we'll go over the demonstration tests. The first of the set of the tests will be static tests, in which the coil position and supply voltage RMS will be kept constant throughout the whole test. RCAC will only be enabled after the oscillations have stabilized. The purpose of this set of tests is to show that RCAC can adapt under different static system parameters. That is, parameters that may be different but don't change throughout the test. The second test is an auto-tuning test. First, the oscillations will be stabilized at a given coil position and supplied voltage. Then adaptation will be disabled and the controller will be disabled until the oscillations come back. Finally, the controller will be enabled while keeping adaptation disabled. It will be shown that the previously obtained controller coefficients are able to stabilize the oscillations. The purpose of this test is to show that RCAC can obtain controller coefficients that can be used in subsequent tests without need for further adaptation. Finally, a dynamic test will be performed. First, the oscillations will be stabilized at a given coil position and supply voltage. Then the coil position will be changed to a position of more complex oscillation. That is, a position closer to the lower quarter of the tube. Next, adaptation and the controller will be disabled to let the oscillation fully come back. Then the controller will be enabled while maintaining the adaptation disabled, and the oscillations won't be suppressed. Finally, adaptation will be enabled again and the oscillations will be stabilized. The purpose of this test is to show that RCAC can readapt the controller coefficients to account for dynamic system parameter changes. Finally, these are the references I mentioned during the presentation. This is the end of the presentation. Now we will proceed to the practical demonstration.